Some important facts about this process and even more pointedly about the two forms that we end up with. First of all, the REF, the row echelon form, is not unique. If you implement your own choice of row operations, of sequence of row operations, and I do mine and someone else does theirs, we may come up with different REF forms. Okay, so it really depends on which row operation, which steps we decided to do. Okay. However, there is some information which is contained in the REF which is unique to the system. What information is there? For instance, the number of non-zero rows is always going to be the same. We're going to call this the rank of the matrix. We can also call it the rank of the system. However, later on our focus is going to shift primarily to matrices, and we're going to see that matrices are really a very general tool, and the linear systems are just one of the applications of matrices. Okay, so we're going to usually associate the word rank to the matrix rather than the system, although we can do both. Okay, so this is not going to change. If you get your REF, I get mine, and someone else gets theirs, we may end up with different REFs, but all of our REFs will end up with the same number of non-zero rows, therefore with the same number of leading coefficients. Okay? So the number of leading coefficients therefore is going to be the same because that corresponds to the number of non-zero rows. Okay? So the number of leading coefficients is also called the rank of the matrix. Okay? The variables actually that contain leading coefficients, remember each column of the matrix, except for the last one which indicates constants, but each column of the matrix corresponds to a variable. Well, if that variable has a leading coefficient associated with it, it's called a basic variable. And if the variable does not have a leading coefficient, it's called a free variable or a parameter. The reason for that is that the variables that correspond to columns that don't have a leading coefficient can be given any value that we want in the solution. The other ones, the basic variables, are the ones which are subject to them. Let me show a little example. Let's say that we have gone all the way to the REF of our system, and this is the REF that we end up. Okay, so remember, from a system we construct the augmented matrix, then we do row operations according to the strategy that I've outlined. We come up with this. Okay, so first of all, what kind of form is this? Well, again, this is an REF form. It's not an RREF. It's not a reduced row echelon form for a number of reasons. For one thing, there are lots of numbers above leading coefficients which are not 0, and 3 of the leading coefficients are not 1. So it's definitely not a reduced row echelon form. Okay, but we can tell that the rank is 5, right? Each one of those 5 rows has a leading coefficient. There's a 1, a 7, a 4, a 7, and a 1. So we have 5 of them, so the rank is 5. Here is something else that the REF can tell us, even though it is not unique. Ask yourself, is this system consistent? Well, just look at the last row. The last row reads 0 equal 1. Well, that means that, of course, is a false statement, which means that no matter what value we give to our variables, this system is going to be false, and therefore that means that this thing does not have any solutions. This is something, notice, that we got from the REF without actually knowing anything even either about the original system or about the RREF. So this is another piece of information that we can get straight from the row echelon form. Now, if that last constant, in fact, that leading coefficient of the last row happens to be a 0, then yes, this system does become consistent, and it starts now and ends up that it has a rank of 4, right? We've lost the row completely. Again, we're going to see all these situations through examples in class, and there is many situations that can occur. Okay. Now, in this particular situation, which ones are the leading variables or the basic variables? Leading variables is another name for basic variables. Okay. Well, of course, the first one, the second one, the fourth one, and the fifth one, which are the ones which have leading coefficients. Now, notice that the leading coefficient is not 1 yet because we're not in RREF form yet, but we know that at the end, the leading variables, the basic variables, will be the first, the second, the fourth, and the fifth. On the other hand, the free variable will be the third one. Okay? The third one does not have a leading coefficient, therefore it can be whatever it wants. Okay? So that's also going to be called the parameter. Now let's have more little thoughts, but important thoughts, and this time about the reduced row echelon form. This one, in fact, is unique. Okay, so if we start from a system and we construct this augmented matrix, and then we go all the way to the reduced row echelon form, if we've done the calculations correctly, we're all going to come up with the same matrix. Why is that? Because remember that reduced row echelon form is the form in which we can read the solutions explicitly, and of course the solution is going to be the same since we're starting from the same system. So because the RREF shows us explicitly what the solutions are, then it is unique. Now, one word of warning: a system may have many solutions. Remember, we talked about that. Sometimes it has infinitely many solutions. In fact, if you go back through what I've said in this class, you'll convince yourself of why what I said earlier is true, namely that a linear system either has no solutions or one solution or infinitely many solutions, but it cannot have 2 or 3 or 25 solutions. Okay, but in anyway, whatever the solution set is, that solution set as a set is unique. Therefore, the RREF is going to be unique. Now, one little final word of terminology: a system whose vector of constants is 0, so in other words where the constants are all 0, is called homogeneous, and these homogeneous systems will be playing a very big role later on, as well as the homogeneous matrices. Okay, so well, mostly homogeneous systems. Now, of course, a system like that always is consistent, because, well, can you think of what the solution is? Well, if all the constants are going to be 0, all I have to do is to get a solution is set all the x's to be 0, right? All the variables. So this particular solution, which always exists for a homogeneous system, is called the trivial solution. But the problem for a homogeneous system usually is, does it have other solutions? Okay, so we know that it always has the trivial solution, and therefore we're going to be studying whether it has other solutions or not.